Hello, good morning.
Good morning. Good morning, Dr. Sira Ramirez. How are you?
Fine, how are things going?
Very good. Very good.
Do you know if the university is officially open? I just walked into my lab a few days ago.
Oh, you did?
Oh, okay.
Uh,
The door was open in the side street and I just entered.
oh, okay. I think entering your office is no problem. It's the research lab. There's some restrictions.
Yes.
Uh, and my student, I sent you an email. I don't know if you receive it. Give you update. Who is the one in charge? And he has.
Okay. Yeah, I spoke to him.
Okay.
I spoke to him. Okay.
Yeah.
He says he's going almost regularly to the lab.
Right. So it's gradually reopening, but in the summer, only professors, visitors, and graduate students, not undergraduate students.
Somebody's playing music.
Yeah. If you right click on my picture, you can make me a co-host, and I can manage it for you.
It says make you host, not co-host.
Okay.
Oh, I will silence the audio. Okay. Oh, now I can hear. It doesn't give me the option of co-hosting, only hosting.
Right? You can make me a co-host or host. There you go.
Okay.
And
Okay. Good. Welcome. Let's continue with our exposition of the structural aspects of nonlinear discrete time system.
Oh, Professor, do you want to record the meeting?
Pardon?
Do you want to record it?
Oh, yeah. It's not recording?
Not yet.
The video is going on.
Oh, okay. Yeah, now it's recording now. Yeah.
All right. Let's continue with our exploration of the structural aspects of discrete time nonlinear systems. One of the key issues there in an input to state model and provided with an output function is to determine the structure linking the inputs and the outputs. This structure is the first step in establishing structural properties which are invariant and the feedback. And we saw that one of those concepts was the relative degree, and that the definition of the relative degree allowed for a state coordinate transformation that would give you two portions of the system, the linearizable portion, linking the input to the output. And for that, we only required a partial state feedback in the sense that a new control input could be admitted so that we had the possibilities of now continuing with our control objective in the linear arena. And the other issue that emerged right from there is the existence of some dynamics which is complementary to the input-output dynamics. This dynamics is known as the remaining dynamics or the hidden dynamics or the zero dynamics. And the stability of that dynamics was crucial for the success of the control scheme that we try to design on the input-output relation being now a simple linear structure. So for systems in which that stability is adverse, like non-minimum phase, that's the name we give it to it, then our control design could be jeopardized by that instability. Even though in principle you cannot see the immediate effects of that instability in the output, because the output is somehow decoupled from these dynamics. Control depends on the variables defining that zero dynamics, and therefore the control design is very much attached to the characteristics of that zero dynamics. Let me give you another example of a landing spacecraft. What we have in mind is something like this. It's a very simple physical example in which Newton's second law is applied, but with a varying mass. You have a landing spacecraft which is exercising some force due to the expulsion of gases at very high velocity. And you're interested in diminishing the height of this spacecraft and arrive at the zero level of the surface with zero velocity or very small velocity, so that you can safely shut off the motor and then descend for 1 meter or so into the surface with no force being applied. That is a typical control problem, and Newton's second law can be directly applied. Let me give you a short preview of the model. The model comes from the sampling of a nonlinear system, and that nonlinear system is just a response to is a representation of Newton's second law. So for instance, x1 represents the height of the spacecraft. So x1 k minus 1 minus x1 of k divided by delta gives you the time derivative and the limit of x1. So that's the velocity. The velocity is called x2. Delta is the sampling interval. So the velocity of descent is x2, and the acceleration, which would be the derivative of x2 in the continuous time case, would be the difference of these two terms divided by delta. So the acceleration would be the composition of the gravity acceleration positively acting downwards and increasing the velocity in the downwards direction, minus the acceleration due, the braking acceleration due to the action of the motor. The motor is represented, or the motor being on is represented by this control input UK. So UK is going to be modulated between 0 and 1. 0 meaning you're not applying any force, and 1 you're applying full force. And the force is composed of these terms. The terms are sigma, which is the rate of consumption of fuel, and alpha, which is the velocity of the gases being ejected, and x3 is the mass. So the acceleration divided, the force divided by the mass is the acceleration. So acceleration opposes the acceleration of gravity. So this is a standard model, and of course, since the mass is varying, the derivative of the mass, which would be the difference of these two terms divided by delta, is just minus sigma times UK. So it's also modulated by the same control. Sigma is the rate of change of the mass due to the consumption of fuel, and UK is the modulation between 0 and 1. 0, there is no consumption of fuel, and therefore the mass is constant because the derivative of the mass would be 0. Or UK is 1, and then you're expanding the maximum rate of consumption of fuel. So up to here, this is Newton's second law with some varying mass. But now here comes a strange variable, which is not derived from Newton's law. is an extra equation, and the meaning of that will be very clear when we explain it later. But at the time being, let me say that X4 just remembers the immediate past value of X3. So X4 is an extra state variable whose value at time k is the mass X3 at time k minus 1. So the dynamics of that variable satisfies this equation. And as you can see, this is an extra variable that whose meaning seems to be rather strange, but as we previewed in the last lecture, it's going to be needed there for the invertibility of some transformation. So this is a phenomenon that is unique to discrete time systems. You cannot invert sometimes the system, and we will need to do some inversion at some point, unless you have variables that account for the expression present in that inversion. And usually some of the variables that appear in that inversion are past state variables. And even though it is not difficult to implement something in your computer to remember those laws or those variables in the past, nevertheless, from the mathematical viewpoint, you have to be able to resource to those variables at some point. So you have to keep track of what their evolution is. And in this instance, the physical meaning of that is just a recollection of the immediate value of the mass that was obtained in the previous sampling. So this is the model of the lander. The output of the system is just the height that separates the spacecraft from the ground. So if you yes. Okay. So if you take the output as the first, somebody's playing the music. Okay. Okay. There's an option here for silencing.
So you can mute everyone, Professor. You can mute everyone as a host.
Okay. Yeah, that's what I tried to do from here. Okay.
Yeah. Professor John's microphone, please turn it off. Thank you.
Okay. So if you take the output as a first state variable, which is sort of an automatic thing to do with the transformation that establishes the linearity between the input and the output, then the first advance of the position is just the first equation in the system, which is this. So this is the first advance of the output, and the second advance of the output is, if you go through the equations, already contain the presence of the input. So this system is relative degree 2. You only need 2 advances of the output to have the input explicitly appearing in the computations. So the second advance of the output has a partial derivative with respect to u, which is non-zero, and that means the relative degree of this system is 2. And the system is a 4th order system, so you do have the need of complementary variables. So part of the transformation is just to rename the output and the advances of the output as the new coordinates. C1 is Y1, and which happens to be the first state, and C2 is just the advance of that first state, the position variable. Therefore, you call that C2. So this partial transformation gives you a relation which, even though it's nonlinear, it has the enormous advantage of having the presence of the input in an invertible manner so that now the whole advance can be renamed as a new auxiliary control input. This nonlinear expression is nonlinear only because the presence of this x3 in the denominator. All this term you can baptize anew with the name of an additional variable. So v sub k would be the controlling this second order string of delays. And therefore the system becomes linear after the state coordinate transformation and the input coordinate transformation. But since the system is fourth order, you have to find two new variables to describe the rest of the transformation, because the system being fourth order, you have only managed to obtain a second order dynamics which is feedback linearizable. But the other two variables have to be complementary variables in order to complete the transformation. So this part is the linearizable part. It's even though this seems like a complicated expression, thanks to the presence of the input, all this is replaceable by a single control input. And when we do the design of this very simple two delay system or two forward step system, then we can recompute the control from our design exercise on the basis of an auxiliary control input. And now the issue of completing the transformation, well, we might even take as the other two variables exactly the same original variables. There is nothing wrong with that. The only inconvenience that appears in taking those complementary variables as the original variables mass and x and this strange variable x4 is that in the variables describing the dynamics which is foreign to the input-output linearization is that the presence of the control is there. And the presence of the control is not a big obstacle to do the analysis. The only thing is that when you use some control here to regulate the linearizable part, in order to study the stability of this system, you have to replace the very same control in this equation. And therefore, the analysis is a little bit more complicated, but it's not something that represents a real obstacle. So in this essence, this is our canonical form. The canonical form has a clear linearizable part, which is only second order, and has two extra state variables which will represent the zero dynamics when we make the linearizable part evolve in accordance with our control objectives. Therefore, the zero dynamics has to be analyzed further. Let's see if we can get rid of the presence of this U right here in these zero dynamics variables. We said that it would be possible to obtain some new variables such that their first advance is independent of the control input. And for that, we will have to change these two variables, C3 and C4, for something else different than X3 and X4. And in order to do that, of course, we can eliminate the control from here by let's say, resorting to these two variables, C2 and C3, because they both contain the control. And there is some combination of these two variables which can eliminate the control, because I need only to multiply and divide by certain functions to obtain the same expression here, and then cancel them. And of course, the first advance of that new variable will not have the presence of the control because we have eliminated it. And it doesn't matter if we use these two variables or the original variables in the model, x2 and x3. It's perfectly legal. We can always eliminate u from x2 and x3 to call that the new variable that will occupy this position. And x4 can be left alone, except that if x3 is changed, then x4 has to be changed. And that can be done. So for instance, we can define eta 1 as this combination of x2 and x3 through x4. If we do that, and we retain x4 as the second variable for the zero dynamics, eta 1 and eta 2 are going to be the variables attached to the zero dynamics. Eta 2 is now of such nature that its next advance does not depend on the control, because we have managed to create a combination of x2 and x3 through x4, so that the next advance of eta 1 is independent of u, and that can be seen here. If you compute eta 1 at the next instant of time, you propagate x2, and that contains still x2, as you can see, x2 contains x2. So it will appear there, and you will have the nonlinearities appearing, and you will have to subtract the next value of this quotient, which is x3k plus 1 over x4k plus 1. The advance of this quotient is the quotient of the advances. So when you simplify this expression, the control disappears. And that's a nice thing to have, because now the zero dynamics attached to eta 1 is completely independent of the control input. But the transformation has a little bit of a problem. If we didn't have x4, remember x4 of k, according to a definition of x4 of k is the previous value of the mass. If that variable was not there, because Newton's law doesn't demand you to remember anything, if that variable were not there, then you wouldn't have been able to do the transformation and to get rid of the control. What it means is that in sometimes performing some operations in order to have the canonical form in a more convenient manner, you not always have the invertibility guaranteed unless some variables exist already in the system that can describe that invertibility. And this is precisely what happens here. And it will also happen in the linearization. And the boost example is one of the cases in which you cannot do the transformation because you need extra state variables. And that increases the order of the system. And the system is no longer state feedback linearizable because the entire dynamics has to be linear. And here you will be left with some zero dynamics again, even though it is a not inconvenient zero dynamic. So when we incorporate the presence of this extra variable, now we can write the equation for eta 1 and eta 2. Eta 1 is just a function of the linearizable states and some constants, delta and the gravity and alpha, which is the velocity of the gases being expelled by the spacecraft. And eta 2 of k plus 1, which was x4, gets transformed into x3 of k, which now has to have a different form in terms of the linearizable variables, and in this case, the first variable associated with the zero dynamics. So the zero dynamics now, it's a function, I mean, the variables associated with the zero dynamics are scalar functions whose first advance is completely independent of the control input. And now you can study the stability of this subsystem in a sort of a standard manner, because no longer you have to substitute here any control input. So it's an autonomous kind of system. This system, however, in the transformed canonical form, you have the clear exposition of a linearizable dynamics, and here you have the zero dynamics. This zero dynamics is unstable, because when C1, which is the height, is stabilized to a constant value, let's say 1 meter of height, or very close to zero, then, you know, from a practical viewpoint, you don't want to stabilize at zero because you can have some overshoot, and that will mean that you will hit the ground with some speed. So it's better to stabilize the whole spacecraft to, let's say, 1 meter of height. And if you have a little overshoot, then you still be safe. And it's no problem in shutting the control off at 1 meter of height in a planet that doesn't have too much gravity. That doesn't mean you will have a big crash, but you will have a descent which is relatively slow. So in the linearizable part is very nice, very easy to control by means of an input coordinate transformation that will render the system completely linear and controllable. But the zero dynamics is given by these two variables, which is now independent of the control input. And let's see that this zero dynamics is unstable, because if C1 is stabilized to a constant value and the velocity goes to 0, when you substitute those values here, C1 equals 0 maybe, or 1, and C2 equals 0, this becomes constant. All these are constant. All these constants tell you that eta 1 will continue to be a constant, but eta 2 will be growing somehow, because eta 2 of k plus 1 has this eigenvalue, and if you linearize these dynamics, eta 1 is going to a constant value, all this is going to a constant value. The velocity of the gases determine very much the zero dynamics if this is 0, and eta 1 is the value of the zero dynamic, which is constant. And that constant might be greater than 1, and you have an unstable zero dynamics. But in this essence, the zero dynamics will bring you the behavior of the remaining dynamics when you have a hovering maneuver over that planet and your height has been managed to be stabilized at a constant value. Then, of course, what happens physically is that you're still burning fuel. And so the fuel, which is directly connected to the mass, will start decreasing. The mass will start decreasing because the mass of the fuel is decreasing. And if you keep that height to be a constant for a long time, you might run into the problem of depleting completely the fuel. Therefore, the dynamics associated with the mass of the system is being unstable, in the sense that it's decreasing without any control, because your control objective was to keep the spacecraft hovering at a very small height, let's say, and you over exceeded the amount of time that you needed to be there just to land. And therefore, your zero dynamics is going unstable, and you might deplete the whole fuel mass, but the mathematics will tell you that the whole mass is going to 0, which is because we didn't separate the mass, the dead mass of the spacecraft from the mass of the fuel. But that's what's going on. The mass is decreasing, and that's an instability of the zero dynamics. And sooner or later, you will deplete the fuel mass, and the control will go to 0 by itself, because there is no control force being applied to your spacecraft, and then you will be forced to land with no fuel remaining for your trip back home. Therefore, the zero dynamics will tell you what provisions you should be taking in order to guarantee enough fuel for the return trip. And that of course, comes from the analysis that you can do on this set of equations, whether in discrete time or in continuous time. Is there any question about this example?
大家有什么问题没有？可以问一问。I guess not, Professor. Please proceed.
Okay, thank you.
Thank you for asking.
Okay. Let's explore another structural issue of nonlinear discrete time systems, especially when you have some disturbances affecting your state dynamics. Let's assume for the moment that you don't have any disturbance on the output. But in the state equation, you have the presence of the control input, trying to control your system, and you also have the presence of some disturbance. We will analyze the structural aspect of this disturbance in the following manner. The control input is something that you willfully apply to the system in order to obtain some objective. And it's an input that depends only on your choice of feedback and depends only on your willing to sustain that input. The disturbance is also an input, but it's an input that you do not willfully apply to the system. Nature applies that input to your system, and usually in an adverse manner, in the sense that whatever nature is doing with that input being applied to your system sort of counteracts or tries to counteract whatever objective you are setting yourself to obtain by means of the willful control action. Therefore, the disturbances in this instance are considered to be inputs, but they are inputs which are being applied in a foreign manner to the system by an intelligence that has different objectives than yours. And therefore, the presence of this disturbance is not always beneficial to your objectives. They might be in contradiction with your objectives. Sometimes those disturbances sort of help you a little bit out, but that's a very strange case. So let's assume that you have now in your dynamics the presence of these two inputs. One, which is the input you can control and you can prescribe, and another one which is foreign to the system that you cannot control. And in essence, these two inputs are independent. Of course, some disturbances might be dependent on the state. It doesn't matter. It's something that you don't fully understand, and you don't have the full structure of that in order to know how to counteract that. So the only option you have is to analyze the structural aspects in order to see under what circumstances this additional input might be bothering you in a manner that you cannot accept, or on the contrary, that you might forget about. And let's see the possible cases. So as inputs with affecting the system and the presence of an output that you have already chosen or that the system is allowing you have possibly two relative degrees. One is the relative degree of the control input associated with the output. So the relation between the output and the input is measured via a relative degree. But since you have another input, you have to think about another relative degree, which is the one linking the same output with this foreign input. So basically, the relation linking the output to the input U or to the input Xi is a two input to one output relation. And both inputs might exhibit with this output a different relative degree. In principle, that is valid. If you start taking advances of the output, you define the relative degree with respect to the input when you hit the explicit presence of the input in those advances. And then two things might have happened. Either in those advances, you already found the explicit presence of this input Xi or not. And in those two cases, and the limiting boarding case, we will set up our analysis for this relation. And our objective is to establish when can you claim that there is some decoupling from this disturbance or of this disturbance from the input-output linearization, which is the whole reason behind the transformation that we are advocating at this point. So we clearly have three cases. The relative degree of H with respect to U is smaller than the relative degree of H with respect to C. This is one case. Second case, the contrary happens. The relative degree of U is larger than the relative degree of H with respect to C, to the foreign input C. And the borderline case is the one in which both relative degrees are the same. So let's analyze slightly the three cases. The first case tells you that when you start taking advances of the output, when the input appears, the presence, the explicit presence of the disturbance was already there. So if it takes R advances of the output to obtain the explicit presence of the input, in less than R advances, the disturbance appears in the expressions of the advances of the output. What it means is that that presence of the output precludes you from establishing a state coordinate transformation which is viable. Why? Because at some point, the new coordinate that you find depends on the perturbation. And therefore, for that new coordinate, you need to know this perturbation in order to continue with the advances of the output, because the next output is also going to contain that perturbation and possibly in an advanced manner. And therefore, the state coordinate transformation that we need to exhibit the linearization between input and output is clouded by the presence of the disturbance, and the presence of the disturbance demand the knowledge of it in order to define the transformation. So this case is not viable. And if you're willing to use state coordinate transformations, ignoring the presence of that disturbance, at some point, you won't even know if you can invert the transformation, and you will start wondering why the coordinates, which were cleanly a function of the advanced output, start behaving in a weird manner. And that's because in their definition, the presence of this disturbance was there. And since you don't know that disturbance, you cannot implement this transformation. Therefore, this case is out of consideration. The relative degree of U, the relative degree of the output with respect to the control U being smaller than the relative degree of the output with respect to C, means that you cannot linearize the input-output relation in a manner which is totally independent of the disturbance. Therefore, that case collapses because of your inability to prescribe the state coordinate transformation. And that's the first case. The second case is, okay, you have the opposite situation. The advances of the output up to some point, let's say R, suddenly exhibit the presence of the input. That's a well-defined operation. And in that relation, in those advances, you never heard of the presence of the disturbance. So your input-output linearization as part of this partial state feedback transformation is now completely viable. And the presence of the disturbance will be necessarily attached to the variables that describe the zero dynamics. So the disturbance has nowhere to go except to hide itself in the zero dynamics variables, the definition of the zero dynamics variable, which make it difficult to analyze the stability of the zero dynamics, because in order to prescribe those variables that you know are affected now by the presence of the disturbance because it never appeared in the input-output relation, is not giving you a clue on how to proceed with that part of the complementary transformation. But it's okay, it's not bothering you between the input and output relation. The only thing that might be happening with this is that either it has an adverse effect on the stability of the zero dynamics. Those perturbations might be affecting the stability of the zero dynamics, and that will result in a non-minimum phase system, which is now unstable, not because of the structural properties, but it is unstable because of the presence of a disturbance that might be destabilizing your equilibrium of the zero dynamics. On the other hand, it may also happen that this disturbance disturbs in a bounded manner the equilibrium of the zero dynamics, and you are oscillating around the equilibrium point with bounded values of the zero dynamics. Well, that doesn't bother you in the output relation. So this is the second case. In this case, you're still able to establish the linearization and provide with a design that stabilizes the output, but you have to be conscious that the zero dynamics is now getting to be a little bit more complicated because of the confined presence of the disturbance in those variables described in the complementary dimensions of the input-output linearized system. And therefore, structurally, this is something that is happening. But at least you're safe for your design as long as you can demonstrate that the zero dynamics is not being adversely affecting the stability of your zero dynamics or the minimum phase character of your zero dynamics. And the third possibility, which is very interesting and which will be used by us in the subsequent things that we will be doing with active disturbance rejection control, is that the relative degree of the control input is equal to the relative degree of the output of the input C of the disturbance input. In that case, the same number of advances of the input all of a sudden will contain the input U and the disturbance C. So the disturbance is very much acting in the same manner, at least structurally speaking, as the control input, in the sense that they appear in the same advance of the output and not at different advances of the output as in these two previous cases. So what can be done from there is that at least the control has the presence of the disturbance, let's say in a channel that is synchronized in time with the disturbance. And in principle, there should be something that you could do about it. And this is one of the issues which is very relevant in active disturbance rejection control. So the essence of this will be the control may be able to counteract the influence of the linearizable dynamics in the feedback in order to counteract or diminish or somehow make smaller the influence of the disturbance in the closed loop system. Attenuation will be possibly one of the options, or estimation and canceling, as it is done in active disturbance rejection. So let's see what happens mathematically with the last case, which seems to be the most interesting, because the first case is of the impossible type. The second case, there is a big question mark about the stability. And the third case, which is the frontier between the two previous cases, corresponds to the same relative degree. So the theorem that characterizes that borderline case is that a perturbed n-dimensional system, nonlinear system, which is relative degree n, is disturbance decoupled if and only if the partial derivative of the state map with respect to the disturbance is found in the span of the vector obtained by the partial derivative of the next state map with respect to U. And in this case, we say the relative degree is n because it might be r, but it's the same relative degree for the two of them. So let's assume that there is no zero dynamics, and therefore the disturbance cannot be in any complementary variables because there are not complementary variables in the case of relative degree n. And therefore the disturbance, in order to make the linearization viable, has to appear in the same equation where the control appears, which is the last equation. So if that is the case, then this is the geometric picture that the vector representing the preferred direction of the control input influence on the state is in a subspace which finds there the presence of the disturbance in the same manner as a vector pointed in the same direction. So in the definition of the relative degree, the gradient vector of the output times the partial derivative of the state map with respect to u is 0. The second advance of the output does not contain the influence of the control, and so on. And there is in the last step of the advance of the output, you will have the influence of the control input because the triple product of this gradient times this matrix times this vector gives you a scalar function alpha of x. So this will tell you that the control input is relative degree, let's say n. And let's assume that the disturbance C is also relative degree n for that given output, for the same output that you are considering, the only output that has the system. So all the projections of this vector on the gradient of the output matrix give you a zero components, except the last one in the same manner that the control input does. So the input and the disturbance exhibit the same dynamic degree in reference to the output. Therefore, if En represents the unit vector in n dimensions with pointing in the last coordinate, all these, the product of this matrix constituted by these row vectors times this column vector gives you this vector, in which alpha of x is just the relation linking the input and the output. This is, in some books, this is called the controllability of the system, this particular scalar factor. So if that factor is 0, it means the control input will never appear in your system. So uncontrollable systems are characterized by the fact that this alpha is 0. Therefore, you have the same input-output structure from the actual input and the disturbance input. And if that is the case, then of course you can, because these two vectors only differ by a factor alpha or beta, you can actually put the input vector in terms of the inverse of this. This map would be invertible because the system has relative degree n, and we show that all the gradients of the observability matrix, that means the Jacobian of the observability matrix, is invertible. So you can put both vectors in terms of in the same direction, and therefore they have to be proportional. So the partial derivative of the state of the next state map with respect to the disturbance is proportional to a meromorphic function with respect to the vector obtained by the partial derivative of the next state with respect to the input. We usually call this the input channel, and this is the disturbance channel in a linearized sort of fashion. But the relation between of them clearly tells you that this variable is in the span of the other vector. This vector is in the same direction, possibly in the same one-dimensional space as phi sub u, it might be longer than phi sub u, smaller than phi sub u, or even pointing in the opposite direction, but they are in the same span. Therefore, this is a structural property. And if this condition is satisfied, of course, we're in the case of having the same relative degree of both inputs. Therefore, sufficiently is clear. And in this case, then, this property is telling you that whatever the disturbance is doing is, in a geometric sense, aligned with what the control is doing. And if that alignment is valid, that means that there should be something that the control action should be able to do in order to attenuate the effects of the disturbance, at least in this simplified manner. And that condition of alignability between this sort of input channel and this sort of disturbance channel, that alignability is necessary and sufficient for them to have the same relative degree. And therefore, a structural condition appears on the class of admissible disturbances that affect your system. They have to be in the same channel as the control input. They sort of have to have, even though the influence might be adverse, the influences have to be sort of in the same kind of nature that the control uses to influence the system state motions. And that structural condition is pretty well known. It's called the matching condition. And it means then that alignability, that structural possibility of acting disturbance and control in a similar manner. And when you examine let's say the tangential space to your incipient motions of the state, they are both pointed in the same subspace, although the directions can be completely different. Therefore, it's a structural condition. As you can see, from all the freedom that the disturbance has for acting, this is quite restrictive, because what we're demanding for that matching to happen is that of all the possible freedom directions that the disturbance has in order to act, it has to sort of align itself, has to lay down in the same route that the control is trying to pursue. And in that one-dimensional space, it might be exercising an adverse effect or a temporarily helping effect. You'll never know until you run some experiments or you do a further analysis of the situation. So structurally speaking, this is out of n dimensions. There has to be a preferred dimension in which both the control and the disturbance seem to be acting in a synchronous or matched manner. And that gives you an idea of the difficulty of guaranteeing precisely that condition. Of course, in practice, it is very easy to see when that condition happens or not. For instance, you have a DC motor. The DC motor has two equations, in discrete time or in continuous time. But the control input enters the electric equation of the armature circuit. And that's one dimension of the two-dimensional state of the DC motor. And the torque inputs, the disturbance, the load torque comes into the mechanical equation, which is a different coordinate from the electrical equation. The mechanical part of the system admits the disturbance load torques. while the control, which is a voltage, is acting in a different channel, is acting in the electrical channel. Therefore, in something as simple as a DC motor, which is linear, the matching condition is clearly not satisfied. So whatever disturbances are affecting the load, you will not be able to compensate it immediately from the control. But of course, engineers are very smart, and what the trick that they play is that they suppress the electrical dynamics because they say it's much faster than the mechanical part. And therefore, they establish an algebraic relation between the input and the mechanical part represented by the angular velocity and the torque constant or the electric constant. And with that algebraic relation, they substitute this relation in the second equation, and now everything is matched. So that should teach us a lesson, and the lesson is, from input-output relations, you always have the matching condition satisfied. And this is why it's important sometimes, in order to do design, to resort to the input-output relations. And in the topic that we're studying, the input-output relation is guaranteed to be linear. Therefore, if you have an input-output relation in the form of transfer function or just algebraic equations in advances and the presence of the input there, you can always bring the effects of the disturbances down to that equation. And of course, there will be more complicated influences, but at least they will always be matched. In input-output systems, this is always matched. The matching condition is always present. The other thing that this might be telling you is that it always pays to reduce, as in the case of the DC motor, to carry out a singular perturbation. Singular perturbations sometimes have the benefit of doing the matching condition possible. This is something that is present in many areas of control. The matching condition is important in sliding mode control, for instance. You can show that something like this happens in sliding mode control, and if that condition is not satisfied, no matter how robust you think the sliding mode control is, if this condition is not satisfied, the zero dynamics associated with the sliding mode controller is affected by the disturbance, and therefore you will not as robust as you think. This is one thing. The other area where this is valid is in nonlinear controller design. The zero dynamics, when you cannot push your disturbance to the zero dynamics and it's there, it's present in the same channel as the input, you better have these conditions satisfied in order to be able to guarantee that at least there is something you can do with that disturbance. Remember, this disturbance is not known, and you're fighting against something you don't know, but if structurally you know where is it pointing, then there should be something you can do. This is the morale of this state. Are there any questions about the disturbance decoupling leading to this geometric condition?
Yes, Professor, I have a question.
Yeah.
This matching condition, does this have anything to do with the output, a particular output?
Yeah.
So your whether or not a disturbance is matched, it also depends on the what output you are controlling, right?
Yeah. Yes. It's an input-output relation. It's the consequence of having the same nature of input-output relation between the actual input and the disturbance input to the same output.
Right.
So it is true.
Yeah, so if you look at the input-output relationship, if our goal is to make the disturbance not affecting our output, yeah, that's I think that's where ADRC originally was conceived, the input-output relationship. The state space was used as a computational tool.
Yeah.
Um, but I like what you are presenting here is a more of a generalization of if ADRC is the design goal or disturbance decoupling is the design goal.
Yeah.
This
Yeah.
this is like a formalization of that principle in the state space, right?
Absolutely right. I agree with you 100%.
Okay. Great. Thank you very
Let's
much.
see what Rafael has to ask. He has a question. He raised his hand. Rafael,
Great.
you run? Hi, Rafael.
Professor, could I ask a question that you mean that if the matching condition is correct for the system, satisfied by the system, so the input could be add a bias to compensate the disturbance effect on the system, right? Could I understand your matching condition meaning, right?
Yeah, let me see if I understand your question. You ask if the sorry?
So maybe if the matching condition is right, if for example, if there is no disturbance for the system, the input should be I0. But now I have a disturbance, but the system could satisfy the matching condition. So I could add compensation to the I0 to become I1 to compensate the disturbance for the system. So I could check my targets, right?
Yeah, if the matching condition is satisfied, at least you have the advantage that your control can do something to attenuate the effects of that disturbance in your input-output linearization, which is the main topic in this talks. And what it can do, of course, the process by which this can be done is very clear in active disturbance rejection control, because there is a way to estimate not the disturbance as such, but at least the effect of the disturbance in the equation where the control is. The effect of those disturbances can be estimated. And once you estimate it, approximately, of course, then because you don't have a precise model, an exact model of the disturbance, and therefore a mismatch will always happen. Once you estimate that as accurately as you can, then you can include that in your feedback law in order to compensate or to at least try to approximately eliminate the effects of those disturbances in that equation that is the leading equation in the control of your system, because it contains the only place where the control input is affecting the whole ladder of the state variables that lead you to the output. And therefore, there is something that you should be able to do. I'm sorry. Okay. There is something that you should be able to do. Alternatively, you can think of a transfer function that attenuates that input, so that if you have some frequency information about those disturbances, then you might include in your feedback control something that attenuates the effect of those disturbances appearing in your input equation. If the matching condition is not satisfied and you don't have any control acting currently in the system, then of course the disturbance will be uncompensated. So yeah, it's a geometric condition. It's a yes or no condition, and that is the reason why this is so restrictive. Either this thing is in the span and then you will be able to do something, or is not in the span and you will not be able to control its effects. You will not be able to attenuate its effects. They will either be confined to the zero dynamics or they're going to affect your input-output linearization. And neither of them is entirely desirable, let's say. Is that clear?
Yes, I'm clear. Thank you, Professor.
Rafael has a question.
Yes?
Rafael, you want to go ahead?
Yes.
Pardon?
Thank you very much, Professor. Can you hear me?
Uh-huh. Yes? Yes,
Okay.
I can hear you. Barely, but I can hear you.
Okay, let me increase the volume. What about now?
Yeah, very good.
Better.
Okay, fantastic. I have to admit, the topic of matching and unmatched disturbances is very close to my heart because I had countless heated debates about this topic, especially in the context of ADRC. And I think there is a still a misconception when it comes to this topic, because as you pointed out, this characteristic, this condition is strictly geometrical. And my background is in robotics primarily. And when we talk about matched or unmatched disturbances, when we use the phrase unmatched disturbance in robotics, it means that whatever the system transformation you can do, you still cannot compensate this type of disturbance. And we always use an example of a robot on wheels just driving straight, and there's a disturbance coming from a side, and you have just two wheels. It doesn't matter what kind of transformation you will propose. There's no physical, mechanical way to compensate this type of disturbance. And that is why we call it this type of disturbance unmatched. However, when we start to pile on different types of control problems from power systems, robotics, motion control, I think this term starts to be a little bit blurry. So after this long introduction, my question boils down to, can a system, for example, a DC motor, can it be at the same time, or can this system at the same time have matching disturbances and unmatching disturbances? So it's just a matter of transformation of the system?
Yeah, suppose it's very typical. What you say is true in the DC motor and it's also true in power converters because they have basically a similar structure of transformation of energy from the input to the output. And in this case, is transformation of electrical energy into mechanical energy.
Right.
But suppose you have some low torques, which are strange, either because of friction or because the moving mass, the rotating mass has an eccentricity or something like that. And so your mechanical equation is being affected by the disturbance that you don't precisely know at the moment. You have not run your test, and you notice this disturbance in the mechanical channel. But at the same time, you could be having all sorts of foreign noises affecting your electrical part. So in this instance, you would have disturbances which are affecting both mechanical and electrical components of your system. And you only have one controlling the electrical part. If you simplify your dynamics to a one-dimensional dynamics, then everything becomes matched. Of course, in the case of the electrical motions, the electrical disturbances, they will appear in your mechanical equations in a more complicated manner because a derivative separates them. And then, even though nature is not taking derivatives, you're looking at what the effect of the derivative would be in your mechanical equation. Mm-hmm. Be more horrid than the low frequency disturbance of the mechanical part. So you can have both, but the morale here is this equation, this geometric condition is so difficult to satisfy in practice that either you learn how to live with the disturbances, or you do as much as you can in order to attenuate them. And one way to attenuate them is to relegate them to the same channel, even though that means more complicated disturbances, estimate them. The estimation is going to be approximate. It's never going to be precise, exact estimation of the disturbance because you don't know the model of the disturbance. You cannot have a complete perfect estimation of the disturbance. And of course, the cancellation is also going to be, as a result, suffering from some remaining disturbance of small amplitude that's still bothering you. You learn how to live with that, or you can do as much as you can to relegate that to a more manageable type of effect. But that's true. Does that answer your question?
Yes, it does. If I can follow up, so if we have a system which is subjected to unmatched disturbances, and we decide that we are considering the input-output control problem, not input to state, input to output, can we always, is it always possible to transform our system from the initial unmatched problem to the match problem when we consider input-output control?
Well, you know, if we saw the first case, in the first case, the disturbances enter into the realm of the linearizable variable. So whatever transformation you're trying to apply to linearize the system is going to fail. It's going to fail because those coordinates depend on the disturbance. And they will be there. And you don't know the disturbance. Therefore, that case is hopeless. For me, the case is hopeless. You will have to live with whatever effects you have. And the borderline case in which the control is in front of the disturbance, then it's when you can do something. Then
Can I say something here?
yes.
Yeah, Rafael, you asked a very good question. My understanding is twofold. One is from the input-output relationship perspective, whatever the disturbance affecting the output, that disturbance can always be transformed as the equivalent disturbance in the input channel. And this has been established by the paper of Chen Sen and Professor Yi Huang and so on. I mean, it's a article in Science China, I think from last year. So I think the answer is definitive, yes. But on the other hand, I keep thinking, I mean, this discussion, this heated discussion, I also had with quite a few scholars in the area of disturbance rejection. It always came up. And I keep thinking about in a more constructive way, how do we apply the understanding of matchedness of disturbance to facilitate our control design to make it better. And I think one example, perhaps Professor Li Hui from Shanghai University of Electricity or Electric Power can elaborate on this. If you think about AC motor in motion control, and you think about the line imbalance or whatever disturbances on the electric side, you apply the typical second order ADRC configuration or conceptualization, then that disturbance on the electrical side is matched, but if we ignore that, we treat it as a disturbance on the mechanical side, then our disturbance compensation will be always lagging behind because the disturbance in electricity at least 90 degrees ahead of the mechanical disturbance. So, to deepen the understanding of DRC on the power electronics side, perhaps we have to go into a state space and figure out where does the disturbance enter into the dynamic system and see if the control input can directly cancel that out. So maybe in that framework, in that context, the understanding of matchedness is of critical importance. Thank you.
Absolutely agree. Yeah, the nature of those projected disturbances onto your input channel might take a difficult or complex nature, and that because you don't know the disturbance, you don't know what to expect. But all you can do, at least ADRC gives you a way of dealing with that. Also in passivity-based controls, you just further increase your dissipation, the dissipation of your system in order to attenuate the effect of the unmatched disturbance reflected to your control input span, which is, in the case of passive systems, is also a relative degree 1 type of condition. And it is true. It is true. I believe the fundamentals of this are very well understood, but each particular case, each particular area like mechanical systems, electrical or electronic systems or aerospace systems have their own characteristics that make the general principles sort of be applicable, but with a lot of caution, because the particularities of the area might be such that that you cannot guarantee anything from the mathematical viewpoint.
Anyone else has questions or comments? We have, this is a very important, very intriguing question. Rafael, do you have anything to add to it?
I think just one more thing. I think it's very important because Professor Sira Ramirez very carefully makes a distinction between expressions which I think in literature are used interchangeably, like compensation, rejection, and attenuation. But I think it's very important, especially when we talk about matching, unmatching conditions and nonlinear systems, to make a clear distinction. And I think I have to learn that as well to make a clear distinction, because I'm a victim of using them as synonyms, but clearly they're not.
Thank you, Rafael.
Thank you, Professor.
Yeah, one more thing. On this particular slide, you read toward the bottom, directly counteracting the influence of disturbance input. Professor Ramirez, I think this is how the matchedness or matching condition defined in sliding mode literature, that it's a condition is whether or not you can directly cancel or directly counteracting the influence of disturbance input. And this is this disturbance is physical disturbance, like what Rafael described as a side impact. But this is by no means the total disturbance in the conceptualization of ADRC. Is that correct?
Yeah, I think that's perfectly right, because in sliding mode condition, the output that you're caring about is the sliding surface coordinate function. So the expression of your sliding coordinate in terms of the states. And that's one dimensional, let's say in the case of single input, single output. You have a zero dynamics associated with that output, which is n-1 dimensional. Everything that's affecting your system will be there probably. And if it is there, then it affects your ideal sliding dynamics. When you manage to control your system to the surface or the state to the surface, the dynamics in that manifold is being affected by the disturbance when you have the matching condition. If you do have the matching condition, which is very difficult to satisfy in real terms, practice, because it's an exact condition that demands you to know your system very well and demands you to know the structure that allows the disturbance to come into the state space, then you can actually show that your ideal sliding dynamics is independent of the disturbance. And therefore, there is nothing to worry about. But that's an idealization, of course. In real life, you will have some influence. But that influence, in the case of sliding mode control, is sufficiently attenuated. But it's again, a geometric condition. So the robustness of sliding mode control has to be put into question when you examine the nature of this condition. The nature demands exact knowledge of your exactness of knowledge of the disturbance, how it affects the state space of the system, and therefore you can compute that. But in practice, that's not guaranteed because your model is imperfect.
Yeah. Are there other questions? Are there other student professors want to ask questions? Professor Li Hui, you have any questions or any comments? Because we talk about the electronics, power electronics, and how this might impact our.
Thank you, Professor Go, and thank you, Professor Ramirez, and thank you, Rafael. And I have learned a lot of things from the beginning, and I think I just listening is better, not to give some any questions right now. I'm sorry.
Okay. Great, no problem. Professor 向阳李老师在吗？ Any comments?
Okay, let's. I can go back to the power electronics example and show you precisely what we have in this case. This is, you know, the model of the boost converter. A disturbance can come in the form of a load current. Suppose you have attaching parallel to this resistor, you have a current source that is draining some current from your circuit. That might be a disturbance. That might be the effect of an unknown load that is affecting your system behavior. So that physically, that disturbance is attached to the voltage. And that's one type of disturbance in the dimension of the voltage variable. You might have another disturbances affecting your source. Your source might be the result of a rectification of an alternating current. So your source is not constant. Your source is slightly fluctuating in a periodic manner. So that can be modeled as an additional voltage source that is acting in conjunction with the battery, but alternating with a small amplitude. You have another disturbance affecting this part of the circuit. And this is an ideal model. This is actually made of a diode and a transistor. And the diode and the transistor also exhibit some current and voltage sources that are not taken into account in this ideal model of the switch, taking two positions. Even in the average model of this, those sources appear as sources in series with the control voltage source and the control current source that replaces the switch as an ideal transformer. So you have all sorts of disturbances acting here at the level of the input equations, and the input is in both equations. So the disturbances have to be in both equations in the same manner. And that's not possible. Physically, that's not true, because if you have a disturbance here, that doesn't have to be doing the same things as the disturbance that you're doing here. They're not aligned in any sense. So in this very simple circuit, and this is one of the reasons I love power electronics so much, there are no simpler examples that show you so much complexity. And in that respect, many of the uncertainties surrounding this, which is a model that you can actually measure the components very precisely. There are an enormous amount of sources for the disturbances of unknown nature to be affecting the dynamics of this very simple two-state equations dynamics. Okay, let's go to the next topic. Oh, we're already at the at the end of the hour and a half, but let me continue for a few minutes talking about flatness in nonlinear discrete time systems. Recall that flatness is a property of the state equation. Whatever flatness is present in the system, it has to be in the state equation. And that is one of the reasons why flatness is so intimately related to the notion of controllability. Of course, the way that flatness manifests is in the possibilities of completely linearizing this nonlinear dynamics without any presence of zero dynamics. Total linearization, clean total linearization. Of course, assuming for the time being that your system is not perturbed. So the manifestation of flatness usually comes in the form of an artificial output. That artificial output has the property of being relative degree n with respect to the control input. This is the distinguishing feature, but that's a consequence of the controllability of this equation, or the type of controllability that you can talk about in nonlinear systems. You see, in nonlinear systems, controllability is a local issue. So people rather speak about reachability, local reachability, total reachability, controllability, etc. Are not synonyms, but this is the nature of the nonlinear world. The most you can do to that nonlinear world is to try to make it come closer, as close as you can to the linear world, and define properties there that converge with the properties of the linearized or the linear system, and see if the extension of those concepts to the nonlinear arena is somehow useful. Well, flatness is one such possibility of trying to make these two worlds come to some intersection, some non-empty intersection, or some parallel direction in which you can actually use techniques to control nonlinear systems. So for us, a system will be called difference flat if you can find the scalar function of the state, and this is perhaps a restricted definition of flatness, because some other people allow for the presence of input too, and they distinguish because of the presence of inputs in that output variable to talk about one flatness and two flatness. So in order not to cloud too much the concept, we will stick to the case of static feedback linearization for the time being, which is properly handled in the one-dimensional input case. So we have an output which is independent. This output does not satisfy difference equations by itself. This is a special output that is not autonomous. What we understand by autonomous in nonlinear systems is some state or some nonlinear part of the system, or a function of the state, that will never depend on the control input. no matter what you do with it, if you take derivatives or you take advances, you will never find the control input. That's called an autonomous part of the system, and that corresponds to the uncontrollable part of the system. So Y does not satisfy equations by itself. That's an algebraic statement. It might be very difficult. Sorry?
No, you're fine. Go ahead. A little bit choppy.
Okay. So the output does not satisfy a difference equation by itself. It's an output that if you start taking advances, sooner or later your control will appear. And in this particular case of the flat output, it will appear at the nth advance of the output. This output has the interesting property of being able to parameterize the variables in the system. And there are two types of variables in the system: the state variables, which is a vector of variables, and the control input, which in this case is one dimension. So the inputs and the states can be parameterized in terms of this particular output. It's an artificial output. It doesn't have to be the output of the system. If you have an output of the system, that output is also parameterizable in terms of this output. And what we mean by parameterization? By parameterization, we mean that we will be able to find two functions, let's call them psi and theta sub I. And theta sub I is a vector function with two components. And you will also be able to find finite integers, call them nu and mu, for which the following properties are valid. The state, any of the n states, all the states are parameterizable, can be written in terms of the output that you have found as your flat output and a finite number of advances thereof. And as a consequence of these, the control input can also be written in terms of the same output and a finite number of advances of that output. In the literature, you will find people that establish in a precise manner what they mean by these finite advances and what relation is there between these two integer numbers mu and mu. For us, in a restricted sense, but one which is very useful for examples, the control parameterization will have just one more advance than the state parameterization. And that should be clear from this equation. You see, the state evolution has one difference in time with respect to the control. So whatever parameterizes the states can be put here and in here. And since you will be able to solve for you, the parameterization will be advancing one more time tick of the clock for expressing the input via the same parameterization you use for the states. There will be a time difference. So the state can be parameterized by a finite number of integers or advances of the output. The control needs just one more advance. This is our restricted definition of flatness. There are some works in the literature where people allow this parameterization to depend on previous values of the output. We are not taking that because for us, that means you need to have exogenous feedback. You need to have more variables defining your system equations than what you started out with. So that will be a case to study in dynamical feedback linearization, but not in static feedback linearization. So the flat output has the property of being able to describe completely in terms of advances of its time evolution, all the states in the system and the control inputs in the system too. If there were natural outputs of the systems, those natural outputs of the system would also be parameterizable in the same manner as the state. So you would need the same number of advances because that natural input will be a function of the state, and the state only requires new advances. The natural output will also new advances. Remember, this flat output sometimes is a natural state, but sometimes it's a state that you have to find. It's a combination of states. It's a nonlinear function of the states that you will have to find. You might also need inputs, but we will leave that for the specific case of linear systems, and we will see what the effect of that is. But in essence, our definition can go a long way by saying a flat output is such that it difference parameterizes the state vector components, all of them, and it also difference parameterizes the input variable in a manner such that one more advance of that particular output is needed in the parameterization in the control as compared to the parameterization of the states. So this is the blunt definition of the flat out. Let me give you an example to clear out this definition. This is okay. You raise the hand.
Yeah. So I do have a question here. In the first slide on flatness, y is a function of x. But in the second slide, u is also a function of y. So
yeah,
in your transformation, in your parameterization, is y both function of both the x and u, or just a function of x?
It might be, but in the definition we're advocating at this moment is only a function of x. And that will constrain our nonlinear systems to the class of static feedback linearizable systems.
So you take a u as a parameter in that function? Or?
No, UK is the control input variable, is one-dimensional, and for the time being, it doesn't affect the choice of the flat output. The flat output is only a function of state.
So on the next slide, so it just happened that in this particular parameterization, u can be also solved as a function of y.
Yes. This is what is really confusing. I understand that this is confusing. It's some sort of built invertibility which is possible. X can be of course parameterized in terms of y and its advances. And u can also be parameterized in terms of y and its advances, and it's like this. You will see it in the next example, which is rather simple, how this works out.
Great, thank you.
Give you, and if it's not clear from the example I'm going to give you, just let me know, and we will come back to this. We have state equation. This is a linear state equation, so it's just for illustrative purposes. And you have one control input. And you have your output is x2. In fact, this is a buck converter, and it's a linear. The average mode is a linear converter. But we present it in the form of a discrete time native system. Okay, so the output y2, which is the voltage associated with the capacitor, has the property that is portrayed right here. Let us see how. Remember, the flat output is an artificial output, but it's not a foreign variable to the system. It's an endogenous variable. It's something that can be built in terms of the states and possibly the inputs, but we are excluding the input for the time being. So the output x2 is a flat output. Why? Because certainly from this equation, you can solve for x1 in terms of y, which is x2, and yk plus 1, which is here, and the parameters in the system. So this state is parameterizable by means of y. And x2, which is the output, is precisely yk. So the two states are parameterizable in terms of y. But moreover, since U can be solved from the first equation in terms of the advance of x1, x1, and x2, since x1 and x2 are parameterizable already by means of y, and its advances, U will be parameterizable in terms of y, but you will need one more advance, which you didn't have before. So U is just this linear expression in terms of y. And you can see from here that the flat output is very natural. In this particular case, in which the flat output is the only output of the system, the parameterization of the input gives you the input-output parameterization. And the state parameterization is what is probably new for many people. That the properties of the state evolution and the state properties and the state and the concepts attached to the state can be recast in terms of this output, this special output y. It's not always the case in which the actual output of the system qualifies as a flat output. As we will see in many examples, sometimes you have to compute what the flat output has to be in order to obtain this parameterization of the state and the corresponding parameterization of the input. So here you have this invertibility. You see, you need the output y and certain number of advances which don't go beyond the first advance in order to express the state in terms of y. And U requires two advances, though, so that conforms to the definition we have here. Is this now clear with this simple example?
Yes. Go ahead. Thank you.
Okay. I take that as a yes.
Yes, indeed.
Okay, thank you. All right, so this is the nature of the flat output. These parameterizations are very useful. For instance, you can find out about equilibrium directly in terms of these outputs. You can find input-output properties. You can find stability features. You can find many properties which can help you in your design. Also, in this relation, you know that the important fact here is that the second advance of the output is related to the control input. And if, for instance, you don't have a clear conscience of what the load is that normalized resistor is, you can proceed with ignoring this part and concentrating on this relation and letting this be a disturbance, an exogenous disturbance, a disturbance that depends on the internal variables in the system, in this case, the output voltage and its advance. So what we want to develop is a formalism to be able to systematically assess flatness of nonlinear single input, single output systems. So for that, we will just repeat the concept of relative degree, but push it to the limit of a flat output being a relative degree n function. The fact that the flat output will be a relative degree n output is equivalent to the possibilities of differentially or difference parameterizing the states and the input in terms of that output alone. And well, this will be probably the subject of next lecture. Are there any other questions?
Yeah, any other questions?
Yes.
Professor Zhang, Professor Li? Any
Well, actually, can I ask a tangential question for your matching condition?
Uh-huh.
So that was on, I guess it was page 881.
Okay. Yes.
Well, when you were talking about matching condition, I thought you mentioned the singular perturbation, and also you mentioned the application of DC motor. You said, well, because we understand that for a DC motor, you have both electrical part and mechanical part, and they have a very different time scale. Electrical part possibly in the time scale of millisecond or scores of millisecond, but for the mechanical part, the time scale possibly in the range of seconds. So I understand this part. So you can use singular perturbation. So so basically divide the force scale from the differentiated force scale from the slow scale. But I don't see what is the connection to matching condition here. And also, I thought you mentioned some smart design by electrical engineer, but I thought I missed that part. So what was the ingenious design here?
Yeah. Let me. But I might try to write them down. Let me see if I can explain to you in words. In the particular case of the DC motor, it's clear that when you perform a singular perturbation on the electrical equation, the armature current equation, now you're left with an algebraic equation relating your control input to the so-called electrical torque and possibly the dissipation in the resistor of the armature circuit. You have that algebraic equation is devoid of any dynamics. The electrical torque and the mechanical torque under the same system of units are numerically equal. So the mechanical equation has the mechanical torque constant multiplying the armature current. And the electrical part has the same constant in special units multiplying the angular velocity. Between the two, there is an ideal transformer relationship. So if you take the mechanical torque and the electrical torque, they have to be numerically equal, right? So that there is no loss in the energy conversion.
Well, possible adding some friction torque.
Yeah, the friction torque is present in the mechanical equation.
Or part of the mechanical, yeah, okay, yeah, all right, that's fine.
From the torque
load, from the load, right, I understand.
Okay, so you substitute the torque downstairs, and now you brought the control input to the mechanical equation. Now everything is matched because you're left with a one-dimensional dynamics, mechanical equation. You can do the other way around. And you can bring the torque input to be reflected by means of an algebraic equation into the electrical part. But that requires a different transformation. So many electrical engineers use a simplified model for the DC motor in which inherently a singular perturbation is carried out. And this is how they solve the matching condition. But of course, this is imperfect. This is not a perfect substitution. You are neglecting some dynamics. And they will appear in the performance of your closed loop system. You will see some little spikes here and there coming from the fast dynamics. Yeah, this is the way engineers solved the problem many years ago for the lack of matching of the mechanical disturbances and the electrical control input location. This is how they did it.
Okay.
Yeah, can I understand this in this manner? Since we're talking about motors, by doing singular perturbation, you are separating fast dynamic from slow ones.
Yeah.
And you may discover in the AC motors, for example, that your voltage line fluctuation or line balance fluctuation is on the electrical side. and you are charging the inductor with voltage. So that voltage fluctuation can be canceled by your supply voltage. So that's a cancellation. That's a cancellation on the fast dynamics.
Yeah, it's a cancellation that probably you don't want to spend your control power just to solve a problem of disturbances in the electrical part, because what you're interested is in moving the mechanical part. And that's the objective of your control, to reach a constant angular velocity or to be robust with respect to low disturbances in the form of torques and so on. But it is true, what you say is absolutely true. This practice still used in labs. My students do it all the time. They just simplify the modal dynamics to an algebraic equation and a one-dimensional dynamics.
Yeah, I'm sorry, I have to inject something else here. So the meaning of disturbance decoupling is really going back for a long time. I mean, you go back to 1930s in Soviet Union, they came up with the concept of invariance.
Yeah.
That's what they mean. How do we keep the output invariant when you have different all kind of disturbances? And what we are talking about here is in disturbance decoupling is the same thing, that you have disturbance, and this disturbance is decoupled from not the state, from output.
Yeah.
Because to decouple disturbance from state is a degree of magnitude more difficult. So that's where the all this discussion came in about matched or unmatched.
Yeah.
Yeah. So
yeah.
So really, you can discuss all that if you have an accurate state space model. But in engineering practice, many times you do not have a very accurate model. Therefore, the discussion in state space about the matchedness condition is of a little consequence in terms of practice. The exception of that is the spacecraft, where the model is well defined, and you spend $1 million refining the model, but that's not your regular industrial practice. By and large, in industry, we cannot have accurate mathematical models. We have a rough input-output model, and that's where the formulation of ADRC comes from. Now, I found intriguing in your presentation is you take the idea and you generalize, you formalize it in a very rigorous mathematical manner, that and you tell us what it means in state space.
Yeah.
And I think that's something we can take from here, and we can maybe add more rigor to our thinking and to our discussion. Thank you.
Good. Thank you for the comment. It's quite illuminating, because it is true. This is a condition in the state space. People are married to state space representations for a long time. And what I believe is just one representation that has some advantages and also has some disadvantages. So conditions of this sort are the product of insisting on your state space representation. One of the things that flatness does is to naturally merge the state space representation with an input-output representation, which is useful for design. And the input-output representation, then your problems of mismatching don't have any meaning.
But, I don't know if I interrupt Professor Zhang's question or not.
Oh, that's okay. So yeah, I was listening to your question, but yeah, that's fine.
Okay. And Professor Sadie Shaw and we did some work on singular perturbation analysis of ADRC, and in that work, she was very happy that the geometric interpretation and the differential equation side are consolidating or are validating each other. I don't know if she has any comments to add here. Professor Shaw? Maybe, yeah, go ahead.
Yeah. Yes, let me think about it. Yeah, of course. These matching conditions are really beautiful. Yeah. So, Professor Sira opinion here. So matching for us is you you match the slow and the fast system together and the uniform approximation. So, but when you think about more details
Okay.
here related to that.
Okay.
And control.
Okay.
I'm sorry, Miss.
We still need to help you fix that microphone. It's not very clear. We can hear you, but not very clear. But maybe, yeah, maybe.
Yeah, in the future, maybe I use instead of the computer. So I should dive in. I hope that will help. Maybe.
Okay.
So actually, that triggered me another question. So because here, when we talk about matching conditions, so we consider only the disturbance. But what about the constraints on the control variable u? So for example, for let's talk about DC motor again. So for DC motor, so if your power is drawn from a battery, so that's fine. So you just have a constant voltage. But what if your voltage or your energy is drawn from wall outlet, and then it has to go through some rectification device, so transform the sinusoidal function into ideally it should be flat, but in reality, because you use some capacitor, so it has certain fluctuation. And in the worst case, if you go with some motor design called capless, they're trying to use a very, very thin capacitor to reduce the cost, to reduce the size. In that case, so your voltage, your bus line voltage is basically a half wave sinusoidal sine, the absolute value of sine function. So basically, so that is a very stringent constraint on your control variable u. So do you have any comments on how to deal with this case?
Yeah.
Basically, the constraint on the control variable.
Yeah, the matching condition is a structural condition. It doesn't have much to do with the magnitudes. It is not concerned with who is stronger and how one can overpower the other. It's just the idealization, provided that your model is so correct and so well known, that you can actually establish this geometric relationship in a very clean manner without any considerations for the magnitudes of either the disturbance or the nature of the disturbance or even the frequency components of the disturbance and your ability to cope with that because of saturations and so on. The structural conditions mean something which is in the hidden geometry of your representation. And of course, if aside from that, you have other restrictions and other qualities of your either disturbances of control, on top of this, you would have to examine if you have enough control to counteract the effects of the disturbance of if your disturbance moves from this very exact and comfortable condition that demands a lot of knowledge in order to be able to assess it and to establish it as a fact. So in the examples that you're mentioning, surely the voltage source can come from a number of different devices like rectifiers that have some disturbances because there are periodic things that you cannot rectify. The rectification is not exact. and therefore you have some fluctuation around the mean value. All those aspects which are very important in practice, at least here you have a way to ideally, based on your model, say, okay, I have this condition satisfied. It doesn't mean the whole story. The whole story is that the magnitudes, phases, frequencies are also important. But if this is true, at least in principle, I know a structural aspect that might be helpful. If this is not true, then of course the problem is much more complicated. And at least this approach doesn't give you any clue on how to proceed. This is a take it or leave it condition. It's a yes or no condition. And this is what bothers many people of the matching condition. It's something that is drawn from the state space, and it is true. It's a consequence of your model in a model representation in the state space. When you represent your model in the input-output arena, then all the disturbances, whatever they are, they might be very complicated, but they come, all of them, through the same channel. And what you're interested is in achieving a good performance of your output. And therefore you concentrate on that, given all the possible effects of your disturbances. But that is true. That is true. This only revisits one aspect of the problem.
And this is, like Professor said, the idealization or articulation or abstraction, if you will. When you do abstraction, you always have to leave some imperfection behind. You cannot address all the details in your practical dynamic system, because that will make the theory impossible. So the question is, did we leave anything important behind? That's the question we want to ask. And there's some lessons from history we can learn from. In the 1930s and 40s in the Soviet Union, when they talk about the environments, they talk about idealized environment. They call it absolute environments, where the output is made independent of the disturbance. But at the same time, they recognize the practical limitation of that. So they define another set of environments, delta environment, where the output is not absolutely independent, but the dependency is in a very small degree. So perhaps as we go forward with this, perhaps we can evolve this matching condition, or even the condition of flatness, from absolute, from clear cut 0 to 1, to allow some degree of robustness. And this is particularly true, I think, if you go to the flatness definition. And we have to be very clear on the premise of that definition. The premise of that definition is the relationship between Y and the state is perfectly defined. No ambiguity is allowed. That's my understanding.
Yeah.
Now, if in the future that we encounter a system where that relationship cannot be 100% clear, now is there something else we can do here? But that's in the future. I mean, right now we're not dealing with that level of details. Like I said, we're always leaving some behind, the tediousness of practical systems. We're hoping to establish first a sound theoretical foundation, even with some sacrifice on the assumptions that we make. Otherwise, it's impossible to develop a theory. Thank you.
Completely agree with that. That's a very sensible remark, which puts in perspective every theory has limitations, and it's not different here. Yeah.
Okay.
Thank you for the comment. All right. Thank you very much for listening. We'll see each other next Thursday.
Thank you. Thank you. Thank you.
Take good
thank you.
care. Thank you. Take good
Very
care.
much, Professor.
Thank
All
you.
of
Good
you.
day.
Real pleasure.
Yeah, thank you very much. Excellent lecture. Excellent.
Good.
Yeah.
Bye.
Yeah, take a good rest. Take care. Yeah. Yeah. Take care of
Thank you.
yourself.
Thank you, Professor. Thank you.
Bye-bye.
Bye bye.
Bye-bye.